Okay, can you hear now? Yeah, I think so. Okay, so second session, our speaker is Paulina Goedicke with a categorical model for quantum and classical block designs. So thank you.
Okay. Can you hear me? Oh, great. So, yeah, first of all, this talk is going to be about, I mainly did a master thesis, but I continued working. And I will talk about a categorical model for quantum designs. I will explain in a minute what that means. Outline is the following. I will explain the mathematical background. Then
All right, the audio is coming in and out. Is it possible to use the other microphone?
And then we are going to use the other microphone.
Okay,
I don't know why that's not working. Be a bit more difficult for you.
No worries. Okay, so I will explain the mathematical background, and then I will explain what we did. So this is joint work with Jamie Vickery. I should have said it before, I'm sorry. Yeah, well, the first thing is the design construction, which is a generalized way to put these design structures into categories, and then I will explain how we get a category that encompasses quantum designs with this constructions and also block designs. And in the end, I will explain how to relate these two categories. And then, of course, I will summarize and give an outlook on future directions. So for the mathematical background, so as a motivation, I don't know who of you actually has concrete ideas about block designs. So one example is the Fano plane, which is equivalent to a projective plane of order 2, which can be shown as equivalent to an affine plane of order 2, which again can be shown to be equivalent to mutually orthogonal Latin squares of order 2. And there is a quantum notion for this concept introduced by Vickery, namely quantum Latin squares. And also one can show that these quantum Latin squares can be used to construct AMEE states, which are multipartite quantum states that which density matrix are proportionate to the identity matrix for every bipartition. So, and the goal of the talk is to define a category that has objects that are block designs. So general versions of these things like the Fano plane, and define a category that has objects that are quantum designs, and then to construct a functor between these categories. So as a definition, a block design in general, we call it block design here in the literature. They often call it balanced incomplete block design, but for simplicity, we just refer to it as block design. It's a set V containing V points and a collection B of B subsets called blocks, such that each block has size K, which we call uniformity. Each point is contained in R blocks, which we call regularity, and each 2 points are incident with exactly lambda blocks. So, and we can represent such a block design via an incidence matrix, which fulfills the following conditions. So if we sum over all rows, we get K, that's a uniformity. Regularity is the summing over all columns is equal to R, and lambda balance means that if we multiply the transpose incidence matrix with the incidence matrix, we get the following equation, where E is just the all-one matrix and I refers to the identity matrix. So essentially we get a matrix where every diagonal entry is equal to R and every off-diagonal entry is equal to lambda. So, and given a block design, its parameters relate via the following equations. So in fact, we only need to know 3 parameters to determine the other ones. And these equations will also apply to quantum designs, which I will explain in a minute. So the notion of quantum designs is actually not well defined in the literature because people mean different things when they talk about it. We will talk about quantum designs, how they were introduced by Zauner in his PhD dissertation. And according to him, a quantum design, or quantum VB design, is a set of complex orthogonal projections in a Hilbert space. And these quantum designs can also satisfy certain conditions, uniformity and regularity again. So uniformity means that if we trace out every projector, the trace is equal to R, and regularity means that if we sum over all projectors, we get K times the identity. So, and if we compare this to the classical notion, it's in the classical case, like a block design is a way of partition is set into subsets with certain conditions, and quantum design is a way of partitioning a Hilbert space into subspaces under certain conditions. So, and given a RU quantum design, its degree is the cardinality of the following set, where we build the trace over the product of two projectors that are not equal. And in particular, a quantum design is degree 1 if and only if they exist in lambda in R such that the trace over the product of projectors is not equal to lambda no matter which projectors we choose. This is then like the quantum version of the lambda condition. And as I already said, we can impose similar equations in this case. So given an RU quantum design of degree 1, its parameters relate via these equations again. Yeah, so this was all to the definitions. Now an example. So as an example, we have mutually unbiased bases. These are bases that when we pick two elements of like different bases, the inner product is the same. So a uniform and regular quantum design of degree 2 with parameters R equal to 1, B equal to the dimension of this Hilbert space, V equal to D times K, and lambda is either 1 over D or 0, defines a set of K mutually unbiased bases in a D-dimensional Hilbert space. So in particular, if K is equal to D plus 1, then we have a complete set of mutually unbiased bases. And this is in the quantum information theory community a very interesting or hot topic, I would say. And then finally, I want to explain the following theorem, also given by Zauner. To every commutative RU quantum design of degree 1, one can associate a block design with parameters V, B, R, K, and lambda. So commutative means that all projections commute. So in fact, one can then diagonalize them simultaneously. So I will now explain a bit on some categorical stuff. So one of the main things we will use in our construction is the concept of error categories. And so an error category is given a category C, is the category of its errors, essentially. So objects are just the errors, the morphisms in C, and the morphisms are given by pairs of errors, such that the following diagram commutes. So as an example, the error category of mod n, so the category of matrices and natural numbers, has objects that are n by n matrices of natural numbers, and morphisms are pairs of matrices, such that a similar diagram commutes. Another thing that we will use is the so-called CP construction that is built on the CP condition. This was introduced by Selinger, and this generalizes the notion of completely positive maps into category theory. Completely positive maps are like maps that are positive if we tensor it with the identity on an auxiliary Hilbert space. And positive means it's just a map that takes positive operators to positive operators. And in a categorical way, we can describe it as in a monoidal dagger category as a map between dagger-Frobenius structures. And then this map satisfies the CP condition if the following equation holds. And this essentially means that this map is then completely positive. Yeah. So, okay, sorry, delta is the co-multiplication, so it's doubling, and mu is the multiplication map here. No, I mean, it's... Okay, and then, so as I already pointed out, then there's this theorem by Selinger. So if we have a monoidal dagger category, there's a category CPC in which objects are special symmetric dagger-Frobenius structures in C, and morphisms are morphisms of C that satisfy the CP condition. And as an example, so if we have the category F-Hilb, so the category of finite dimensional Hilbert spaces and bounded linear maps between them, and a set of projections, then we can define a completely positive map from the name of the projection to CB that sends every projection to a computational basis vector. And this map is then a morphism in CP F-Hilb. And I explain that because we can actually encode quantum designs through these CP maps as morphisms in CP F-Hilb, and we will also use that later. So now I'm starting to present our results. So first of all, the design construction. The design construction, it's a bit cumbersome, the definition, I admit. So if we have a faithful monoidal functor between pointed monoidal dagger categories, we can construct this, or like define this design construction as the subcategory of RC, where the morphisms are given by pairs of morphisms such that these morphisms are in the image of the functor F. We can impose some structure on this. So the category BDesign CD is the subcategory of design CD, where objects are regular, uniform, and lambda balanced for some scalars. So in particular, they satisfy the following equations, where the black dot refers to the pointed structure in the category. So if we, so these exactly correspond to regularity, uniformity, and lambda balance condition, and one can in fact prove that these also give rise to similar equations as already stated in the beginning, if we just apply the pointed structure from above and below. So we can prove the following lemma, that we have k times the dimension of D, where the dimension is just the composition of the pointed structure with its dagger, is equal to R times the dimension of A. And this is a more general notion of block designs. So, and with that, if we apply this to the categories mat n and f set, we can define a category BDesign that has objects that are block designs and morphisms that are pairs of functions. And Fz is here the category of finite sets and functions between these sets. We will now talk about the quantum part, and in the quantum part we take the design construction and apply it to CP-F-HILP. So the category QDesign is defined as design CP-F-HILP, and its objects are quantum designs. And then there's also a subcategory, or no, yeah, it's also a subcategory, category that QDesign B, which is just the BDesign construction applied to CP-F-HILP, and its objects are uniform and regular quantum designs of degree 1. So, and this is a more general notion of RU designs of degree 1, as the following example will demonstrate. So one example for this category would be these quantum channels. So if the subcategory QDesign QC, where all objects are CP maps between matrix algebras, fulfilling the following equations, is actually a category of quantum channels with special properties, namely that they also, like, apart from being trace preserving and completely positive, they also satisfy these equations. And in fact, that is ongoing research, how useful that is or how this relates to quantum channels. But there also exists a subcategory of QDesign B that has objects that represent uniform and regular quantum designs of degree 1 according to Zauner's notion. So exactly the ones that we have discussed in the beginning. So in order to prove that, we have to consider this completely positive map that I already sketched in the introduction. And we then find for the uniformity, regularity, and lambda condition these equations. And if we apply the pointed structure again, then we can again recover these equations from the beginning via the lemma that I explained for the design construction. And then there's also a way to put maps into this framework. So if we allow for higher degrees, so not degree 1, but degree 2 in that case, we can also define a subcategory of QDesign, so not QDesign B, because that was restricted to quantum designs with degree 1. And in this subcategory, we have objects that are mutually unbiased bases and morphisms that are pairs of functions. And in order to prove that, we have again considered the following map that's a bit more complicated, but is essentially similar to the case before. And this map satisfies the following equation, where we now have like a more general lambda condition in the bottom row. So, and now for the final part, one can actually relate these two notions via functor. So we state the following theorem: there exists a functor between BDesign and QDesign B that relates a generalized incomplete block design, so to a uniform, regular, and lambda balanced quantum design. And I will skip the proof at this point, but you can read it in our paper. Which is important to stress here is that this is a different relation than the one given by Zauner. So we in fact found a new way to relate block designs to quantum designs using this design construction based on error categories. So to summarize, we developed a construction based on error categories that describes combinatorial designs in a category theoretical context. And then we applied this construction to the categories MAT-N and CPF-FILP and got a categorical generalization of classical block designs, namely BDesign, and a category of quantum designs, namely QDesigns. Then we defined a category MAP that has maps as objects. And we also found a way to relate block designs to quantum designs. Okay, there's a typo, via functor Q. And yeah, there's some open questions left that I consider as worth exploring in the future, and I'm also partly working on. So one would be how do we classify the quantum designs that are also quantum channels, and do they have an application in quantum information theory? That would be actually very interesting to know. Then another is how can we embed Latin squares and quantum Latin squares into these categories? Then how do AMEE states fit into this model? And how are these categories related to the already existing categorical formalism? And in general, how we can relate this to the, or how does that fit into the quantum categorical quantum theory part? So, and finally, another question would be, does a category theoretical point of view provide new insights on the map problem? And this is probably especially interesting for the quantum information community, because this is a widely discussed topic. And with that, I'm done with my talk. Thank you for your attention.
So are there any questions in the audience?
I have one.
Yeah. So please, from the online audience then.
How do I raise my hand?
We can hear you, so please do ask. Tell them that you can.
Yes, so you can just talk.
Go ahead, Bob. We're waiting for you.
Yes.
Oh, me. Hi.
Yeah.
So, I mean, I know that there is some connection between all of these things and SIG POVMs, which is another open problem which Chris Fuchs is particularly keen about. Do you know anything about how this could help with that problem?
Well, so I also worked a bit on that. So there is also a way to put that into this framework, SIG POVMs, but I have not worked that out rigorously, but I guess like it's similar to the map thing.
Thank you.
Okay, are there any other questions? Either here, yeah, Leo.
Okay, thanks. Can you very quickly give some intuition on what's the significance of the existence of this functor that you construct? Like, how do I think about it?
Okay, so one can, like, do you want to know how do you think about the functor, or what we can do with the functor?
Well, I guess what's more useful, like what does it mean that somehow every block design can be translated to our quantum block design?
Okay, so in the way like how the functor is constructed, it shows that, for example, So that's something we conjecture, that doesn't exist a classical block design that gets mapped to a map via the functor. So one could show that, that there's no direct correspondence via the functor, which is interesting for the map problem, I guess.
Okay, but how does it help with the problem, for example, or that's that? I guess that's
that's something I like further
open questions.
explore.
Okay,
Yeah, so
thanks.
but
Thanks.
Thanks. So any other questions, either online or here? Yeah.
So I have a question. I'm not sure if you can see the raised hands.
yes.
Shall I ask my question, or maybe it's someone else?
Yes. Go on, Jamie.
Okay. So I was just going to say that what this does is it puts what this functor does is it potentially puts the space of things that we call quantum designs, and that should include things like MUBs and seek POVMs, into a much more general world where we could find things that are much more general, which are non-commutative, for example. Have you thought much, Paulina, at finding some like really exotic things that would fit this definition of quantum design, which don't correspond to MUBs or things that people already know, but are completely new sort of instances?
Yes, I think we also have some examples of that in the paper.
Okay, but I think, I mean, as a co-author, I'm aware of those examples. I guess I was thinking of things that are even more radical and like.
Yeah. Okay. So more radical ones are that's also ongoing research, but we have one more like basic one in the paper. Yeah.
Okay.
Okay, I'll ask a question maybe also about this functor. Okay. You made the point at near the end that it was different from this other parallel functor by Zauner, I think you said?
Zauner, yeah.
Yeah. So is there a relationship between them? In particular, is there some kind of a natural transformation relating them?
So actually, I haven't thought about the relation, Zauner's relation as a functor. So that would be interesting to think about actually, but so I don't know.
Okay, thank you.
Okay, so let's thank again, Paulina. Our next speaker is Alex Kissinger.
Yeah, so you'll need to stop sharing the screen there.
Yeah, if you can stop sharing, Paulina. So let us a second. And if you have any more questions, you can always ask